Thinking in C, Chapter 6, Programming with Functions.
C is what we call a procedural language because its building block is the function. When you develop a system in C, you usually look at the functionality that you need and you write the functions to do it. So functions are the building block of a C program. Functions obey value semantics, so I'll explain what that means. It's often a good idea to declare your functions before they're used. They either have to be declared or defined, and I'll explain the difference. And the way you declare a function is through a function prototype. Well, once we talk about functions, it'll be important then to talk about scope, the region of visibility of an identifier. And we'll also finish off then by talking about the different types of memory, automatic, static, and global. A function is a named collection of statements, and it has a few key features. First of all, it's defined at file scope. What that means is that all of your functions need to be defined on the topmost level. You can't nest a definition of one function inside of another like you can in, say, Algol or Pascal. Actually, that keeps things simple. It's really a good feature. Since functions all appear at the same file scope, then they all have to have unique names. As you've seen over and over again, functions, the main function that we have seen, is enclosed in braces. And the idea of a function is that it should perform some well-defined operation. You really shouldn't do too many things. It should do something that a single name suggests and has meaning in your program. Functions may take arguments, although we haven't seen an example of that yet, but a function doesn't have to take arguments, just like the main function that we've used so far. Functions can also return a value, but that's optional as well. This program defines a function, avg, to take the average of two integers, and it returns its value as a float. So you can see in the definition here, it says float, that's the return type, avg, the name of the function, but it takes two parameters. So when you call this function, you give it two integer arguments, and it will return the computed average. So in the main program, this is pretty much a repeat of one of the first programs in the course. I'll print out a prompt to read a number and get a second number, and instead of computing the average right there in the main program, I'll call a function to do it. And that's, of course, a nice thing to do. It's nice to divide up your functionality into separate functions. To call a function, all you do is mention its name, and if it takes parameters, then you put those in parentheses. If it doesn't, then you use empty parentheses. It's important that the function avg is either declared or defined before its use in the main program. What I'm doing here is I'm defining it. Defining means you fully give the function along with its body. That's a function definition. It is possible to just declare the name of the function with its return type and its parameter types. We'll see that in a little bit. The point is that the program needs to know when it sees avg down in that printf statement, it needs to know what kind of thing avg is, because it will enforce that you're calling it correctly. Functions in C have value semantics. Another way of saying that is that arguments are passed by value to a function. And what that means is that each formal parameter in a function receives a copy of the argument you call it with. So even if you were to change the value of one of those parameters inside the body of your function, it has no effect whatsoever on the argument that you called it with back in the calling program, in the calling function. When values are returned from a function, the same thing happens. A copy is returned. And what this does is it allows you to embed a function inside of an expression. So in the example we have here, a equals b plus avg of c comma d, the function avg is called, copies of c and d are created, and they become the values of the formal parameters in the function. And then the computed value that is returned comes back in a temporary copy for use in that statement right there. And then when that statement is finished, that temporary copy will go away. The void keyword has two uses in C. One is to specify that a function does not return anything, and so it becomes what other languages call a procedure. So the example here, f, which takes a couple of arguments, Perhaps f is only used then for its side effect, since it's pretty useless. Since it's not returning a value, you want f to do something. Perhaps print things out or write to a file, who knows. Since it's now void, that means that there is no return value. So if you were to try to use x in a context where a value was needed, you would get a compiler error, because the compiler knows that no value is going to be coming back from f. The other purpose of the void keyword in C is to say that you have no arguments. So in the definition of title here, by putting void in parentheses, that means that no parameters are allowed, and so when you call the function title, you're not allowed to put any there. You would just call it with an empty set of parentheses. Here's a function that uses a void return type, print ints. It's simply used for its side effect. Its job is to print out all of the integers in an array, and it prints them with a comma between them. So you pass it an array. Notice I don't put a dimension there in the parameter. That's not necessary. And you also pass it as a second parameter the number of elements in the array. So I have a for loop which goes through each element, and for every element except for the first one, it'll print a comma before it prints it out. You call that function in the main program by just invoking it as a standalone expression, print int a comma 5. As you've already seen, the compiler needs to know about a function before you use it. It needs to know how many arguments and what types of arguments it takes, and it needs to know what its return type is. Unless it has that information, it's an unknown quantity and it doesn't know how to use it. And the nice thing about this is that the compiler will detect any errors. So if you make a mistake and send the wrong kind of parameter or send too many or not enough, the compiler will catch that. And so that's always a good thing. You want the compiler to catch as many errors as you can. It's the runtime errors that are hard to find. So what you need to do is you either need to fully define your functions with their bodies before you use them, as we've seen so far, or you can just list the usage of the function without the body and then define it elsewhere. Now in C, it turns out that it's possible to work around this requirement, but I'm not even going to say much more about that. You shouldn't do it. And in C++ and Java, it's not possible. You must let the compiler know about a function before you use it. So this is a good thing. Another name for a function declaration is a prototype, and basically it's just the function without its body, followed by a semicolon. So this is how the compiler figures out how you're supposed to use a function. The real benefit of this separation of declaration from definition is that it allows you, in a large system, to have header files with a number of function declarations. They'll strictly be prototypes, and that way you can include that file, and now the compiler knows how each function is to be used, and so it can enforce your usage of those functions. And that's what we've been doing all this time with the standard headers. Those standard headers have function declarations in them, and that way the compiler will catch any errors in usage. Basically what happens is that you buy a library or use someone else's library of functions, which has all of the declarations for the functions, and then the bodies themselves will be defined somewhere else, and you may not even get those. You may just get the libraries, the already compiled libraries that you just link with. That's typically what happens when you buy some kind of a commercial library. You get header files and you get some library to link with. This is a rewrite of the average example in the beginning of this section to show how to use a prototype. Instead of actually defining the function with its body before I use it, I'm just going to write down the prototype. The prototype requires a return type, the name of the function, and then the parameter type list. Notice that I'm not using variable names. You can if you want. It's optional. Nothing wrong with it at all. Some people consider it good documentation. But all the compiler needs to know is what are the types of the arguments and their sequence. Having done that, then it's okay for me to call AVG in the program like I did before, and I can put the definition of it later, or, for that matter, in another file. To show you how you might use multiple files in a program, This slide has 3 files on it. The first one, mystuff.h, is just a header, and it will have prototypes. In this case, what I'm doing is I'm taking the average example that we've already seen and I'm dividing it up in the way you typically would do in large programs. So the .h file has the declaration of the function, and then there will be a second implementation file, mystuff.c. And that will have the actual body. It'll be the complete function definition. One thing I didn't show there is that mystuff.c will also include mystuff.h. That's just to make sure you have the definition of the function match its prototype as far as the return type and the parameters are concerned. And then finally, a third file would be my application that uses the mystuff module, as it were. So in fun3.c, I will include, among other things, mystuff.h, and then I can just use the average function, and I just have to make sure that I link with mystuff.c, or I should say the compiled version of mystuff.c, when I build the program. Scope is a very fundamental concept in C. C is what we call a block-scoped language. The scope of a variable, of any identifier, whether it's a data variable or a function name, is the region of your program where it's visible. So it's those places in your program where you can use that name and it has meaning. And there are 3 basic types of scope. We've been using them all along, actually, or at least one of them. We've been using local scope, and that is when you define a variable inside of any block. There are 2 other kinds of scope that we'll talk about. One is file scope. Those are things defined outside of any function. And then there's an extension of that called program scope. There are some others to mention, or at least there's some others that are defined in the language, but we don't need to worry about those at this point. Local scope is so called because it consists of the region between 2 braces. In other words, it's a block. Local scope is what we've been seeing all along. It's the scope that consists of a body of a function, for example. So any variables you define in a function are in that scope. And also any variables that are defined in any other block. For example, a compound statement attached to an if or an else or a loop. So the scope of any such identifier is from its point of declaration until the end of that block. That's the only place where you can see it. And when you leave that block, that identifier is no longer available. File scope is that region of your source which is outside of the function. So anything you define outside of a function is visible from that point that you define it until the end of that file. And functions themselves, the names of the functions that we've been defining, have that same scope, since they're being defined outside of any other function. So once you define a function, you can use it from that point on to the end of your file. You can also define variables at file scope, and sometimes it's important to do that, but let me just mention right now that global variables tend to be a problem. They tend to cause bugs, especially in complex programs. And so you'll see advice from time to time to avoid globals, and that's good advice. And there are alternatives to using global variables in C++ and Java. This example illustrates both local scope, of course we've seen that already, and file scope. The file scope portion is when you can see the int I equals 3 there. It's called a global variable because it's defined outside of any function. Its scope is from its point of declaration to the end of the file. And as we'll see later, this particular global variable is so called because it can even be accessed from another file. But we'll get to that shortly. For now, we just want to look at its role of possessing file scope. So we define this global I, and we initialize it to 3, and then inside of our main program, we're going to print out the value of I. Well, at that first printf statement, there is no other I that has been defined, and so it's going to be referring to the one defined outside. So that will be 3. So the first thing we want to notice from this is that you always have access to anything defined in an enclosing scope, unless you redefine it, which is what we're about to see inside the next loop. So, this for loop goes from 0 to I on loop variable j. And of course, still at that point, the I that is being referred to is the one outside, so it's 3. So this loop is going to go 3 times. 0, 1, and 2 for j. But once we get inside the loop, now we redefine I, or I should say we define another I, and we initialize it with 99. So the effect here is that this nested declaration of I hides the one defined in the enclosing scope. So when we print out the value of I at that point, we're going to get 99. Now, it turns out that you can put a block anywhere you want, and you wouldn't do this very often, but sometimes there are reasons for doing this. The only reason I've got is just to show you local scope. So notice that after the printf statement, I open a block, a freestanding block, and I declare another I, yet another I, and I initialize it with the value of j. Well, this is going to be whatever the current loop index is, of course, and then I'll print that out. So that's the 0 that gets printed out. Now I'll cycle on the loop, and j will get bumped up to 1, but that first I inside the loop is 99, and then the second one will be the loop index again, which is 1, and so it goes in that pattern. Bottom line, an identifier always refers to the deepest definition, and if you define an identifier with the same name as one in an enclosing scope, you hide the one in the enclosing scope. Now we're going to talk about different types of storage. Most of the variables we've seen so far have been automatic variables. An automatic variable, sometimes called a stack variable, is any variable defined inside of a block without the static keyword. I'll explain that in a minute. And so everything we have seen, with the exception of the global variable I in the previous slide, has been an automatic variable. And the main feature of these variables is that they come and go all the time. That's why they're on the stack. When you enter a block, such as a function body, and define variables there locally, they get allocated on the stack, they get used for the execution of that block, and then they go away. The stack pointer gets moved, and those variables are unavailable and in essence don't even exist anymore. And every time you re-enter a block, if there's any initialization you're doing on those variables when you declare them, it gets done anew. In this example, all of the variables are automatic. Even the parameters in the function, because they're allocated on the stack as you come into the function. And I have a local variable named I and small. Notice how small is initialized to nums sub 0, which is the first element in the array that's being passed in. This little function, of course, calculates the minimum of an array. So we initialize the variable small with the first number. And then we go through the rest of the elements, beginning at 1, the second element, all the way through the end. And we just keep track of the smallest as we go, and we return that. All of these are automatic variables. They are allocated on the stack every time you enter this function. Small is reinitialized every time you enter this function with the first element of whatever array you passed it. And then when you leave this function, those variables are unavailable. Static variables, as their name suggests, are variables that persist. In other words, they don't come and go every time you enter or leave a block. To make that happen, they don't reside on the stack. There's a special data area that they go in. It's often called the data segment. At least that's what it's called in DOS and in Unix. And the variables that are static are any variable defined outside of a block. That's one way that you know that a variable is static. And so, in other words, things defined its file scope. And then there's another way also that you can define a static variable. And that is by using the keyword static along with a variable declared inside of a block. So there are two types: outside of any block or inside with the static keyword. And the key feature is that if you have a variable that is static, it keeps its value, even those defined inside of a function. So I guess that brings up the question, when are they initialized? If you have a local variable defined as static within a function, it is not initialized every time you enter that function, because that is what automatic variables do. So in C, static variables are initialized once sometime during the startup of the program before any function in its file is used. This example illustrates a static local variable. The function count declares n as a static integer. That initialization to 0 takes place at program startup. And so the functionality of count is to always return the next integer in sequence. Since n is static, that variable is stored in a special place and it maintains its value during the life of the program. So you can see in the main program, all I do is print out the result of calling count, and by doing it 5 times in a row, I get the numbers 1, 2, 3, 4, 5. Program scope is similar to file scope, except it's bigger. Anything you define outside of a function is going to have program scope unless you restrict it. What this means is that you can access it from another file. So, a couple of slides ago, we had an int I declared outside of any function in its file, and that is a global variable. And the way you know that that is global and not restricted only to its file is because the keyword static was not there. If you want to declare a variable at file scope and yet not have it globally available, that is, it doesn't have program scope so you can see it from other files, you put the keyword static in front of it. I realize that's unfortunate. We're using static for another purpose. That's just the way it is, and if you think that's a problem, well, just wait till you get to C++. There's yet another meaning for static, but we won't worry about that for right now. Static plus file scope for an identifier means it is private to its file. Now the next question is, how do I actually access that global variable from another file? And the way you do that is with the extern keyword, which you'll see in the next slide. This example consists of 2 files, file1.c and file2.c. In file 1, there are 2 variables declared at file scope. One of them is global, that is, it has program scope, and one of them is not. I is global because it does not have the keyword static in front of it. J is private to the file file1.c because of the keyword static. So what that means is I cannot access J from another file, but I can access I. How do I do it? Go down to file2.c. Inside the main function, you'll see the first thing I do is declare I as an extern int. What the keyword extern means is that something is defined elsewhere. Go find it. Basically, it's defined at file scope somewhere. And so what will happen is that this I will become linked to the I defined in file1.c. And so this is a reference to a variable defined elsewhere. If you tried to do the same thing with J, you would get a link error, an unresolved external reference, because that J in file 1 is not visible outside of its file, so there's no way to link to it. For that reason, I have a function called getJ, which allows me just to retrieve its value. So basically what I'm doing is I'm protecting J in file 1 from any change from another file. I only allow you to view it by giving you a function to get it. I do not allow you to have direct access to it. You'll notice that in the prototype for getJ in my main function in file 2, that I did not include the extern keyword. It turns out that's optional for functions. Don't ask me why. It's just a convenience, I think, because you use functions so often. This way you don't have to use the extern keyword over and over again. But for data variables, if you want to link up to global variables defined in another file, you have to use the extern keyword as I've done here. What you just saw in the example on the previous slide is an example of information hiding. The way you do that in C is you declare something at file scope and put static in front of it. And you can do that for both data and for functions. This is really the only way you have of hiding information in C. But it's a good idea, of course. It's nice to have your data protected, and that way you can just offer functions to manipulate that data, but since you wrote the functions, that data is under your control. And this is the key feature of object-oriented programs, and actually came out of the structured programming era of the 80s, this idea of separating interface from implementation detail. It turns out that this is kind of a cheap way of getting information hiding, though. It really isn't as flexible as you might need for real complicated programs. And so C++ and Java and other object-oriented programming languages support information hiding much better. This next example, which takes up several slides, is going to illustrate this idea of information hiding and how useful it can be. What we're going to do is implement a stack. A stack, of course, being a last-in, first-out sequence. And the way we are going to lay this out is in separate files. Stack.h will have the declarations of the functions that do the work. Stack.c will have the bodies of the functions, and it will also have any of the data that I need to implement the stack, but I'm going to make it private so that you cannot access it directly. And then I'll have a test program, tstack.c, which will include stack.h and link with stack.c. But as you'll see, it's only going to call the functions that you have provided me, the interface. And the data is something I have no direct access to. Here's the header file, stack.h. It defines 5 functions, which are commonly needed operations when using a stack. Push, pop, top, which just reveals what's on the top without popping it. Size, telling you how many are in the stack. And I'll also have an error handling function just to let you know if there was a problem or not. And I'm also going to define a special integer code, -32767, which will be my stack error. So I'm going to assume that you will not be using that number as a data value on the stack. This slide has the beginning of the implementation file, stack.c, which has the bodies of the functions, and also the data. Notice the first thing that I do is include stack.h. That's important. This way I guarantee coordination between how I'm defining the files and how they're declared so there's no mistakes. The data that I have, well, max is something that I use here locally. That's protected because it's really not data. Remember what the #define does. It just does text substitution when this file is compiled. So there's no way anybody can access max anywhere because it really doesn't exist after preprocessing. The other variables, error, data, and pointer, are private because of the static keyword. So this is data that I'm using, but no one else can access it directly. And you can go through the implementation here of the various functions. They just do what you would expect them to do. They'll, for example, push here. It checks to make sure that there is room on the stack to add another integer. And if there is, it'll go ahead and add it. Notice the use of the post increment to move my stack pointer through the array. And it'll set error code to 0. Otherwise, it'll set the error code to 1. So the way you use this class is you inquire if there was an error by calling the stack error function, which you'll see in a minute. Here's the implementation for pop and size. Pop is similar to push in that it checks to see if it can do its operation. If you want to pop an integer off the stack, it needs to check and see if there's one there. So it checks to see if pointer is greater than 0. Remember, an index into an array also doubles as how many elements are there. That's the way I'm using pointer to go through the array. So it's really kind of handy. I'll just say if pointer is greater than 0, that means I have elements there. What I want to do in that case then is I want to get the last element. But remember, pointer is pointing at the next open slot, so pointer -1 is the last element that was used. Well, what I'll do here is do the decrement, a pre-decrement on pointer, which will move it, and so now it's pointing at the last data element that was entered in the array, and that's what I want. And as a side effect, it leaves pointer decremented for the next time around. Then I'll set error to 0 and return the value. If there are no elements on the stack, of course, I'll just set the error code, and in this case, I'll return stack error as well. I couldn't do that with push on the previous page because it's void and there is nothing to return. But here I am returning something, and so you can query it immediately to see if there was an error. All stack size has to do is return pointer because that's how many elements are in the array. The implementation of top is similar to that of pop, except it's not going to change the pointer. It just wants to inspect what's there. So instead of using the pre-decrement operator on pointer, I'll simply use the expression pointer -1. Stack error returns the current value of the private variable error, which will either have a 0 if there was no error, or a 1 if there was. Now this is the end of the implementation file. You've seen the implementation of all the functions. Notice that I've used a prefix in front of all of these, stk, so I have stack error, stack top, stack size, stack pop, etc. Well, there's an important reason for that. Remember that all functions are defined at file scope, therefore all the names have to be unique, and one way to make it unique is to make up some prefix. And so that's why I do that, with the hope that there will be no other function in your program, say, with the same name. If there is, you've got a problem, and you'll have to change your name. In this file, I have a main program that tests the stack functions. Notice that the first thing I do is include stack.h, so I have the functions available to me to call. I'm going to purposely put too many numbers on the stack just so I can test the stack error facility. So my first loop will go through and put the numbers 0 through 10, and that's 11 numbers, of course, and that's too many. So the last number will not be put on the stack, and when I call the stack error function, it should return true, a 1, and I'll print out the word stack error. And just to show you that the 11 was not pushed, I'll print out that the last element pushed was, and we would expect it to be, a 9, because there's only room for 10 numbers, 0 through 9, so that 11th number, 10, did not make it. Now to pop the stack, I'll just have a loop that uses stack size as the test to see if there's any elements. While there are elements on the stack, I'll go ahead and print out the result of popping the stack. So that will give me the elements in last in, first out order. And every time I pop the stack, stack size will be decremented. The actual size will be. And so eventually stack size will return to 0, and this loop will eventually quit. If you look at that printf statement, you'll see that I'm printing a space in between the numbers, so they're all appearing on the same line. So in order to have a new line begun, I will call putchar, which is a function that just prints out a single character, and here I'm giving it a new line. Here's the output from the test program on the previous slide, which has the output that you would expect. So to summarize, a function is just a bunch of statements collected together, and it has a name. And that allows you to execute those statements just by using that name whenever you wish. Functions can take arguments, and they can also return values. In C, the arguments you pass to a function are copied into the local parameters in the function. So this is called pass by value, or value semantics, if you will. So just keep that in mind. All of those values that are passed into functions are local copies, and they will make no difference on the original argument in the calling code. A variable, all variables have a scope, but that's just the region of the code where they can be accessed. And a function consists of a scope. A function defines a scope. And so anything you define inside of a function, including the parameters for that function, are only accessible within that function. You can also, of course, define things outside of any function. We typically call those global variables because they can be accessed from other files that are part of the same application. But if you want to have anything that is defined outside of a function not available from any other file in your application, then you just put the keyword static in front of them, and they are now private to that file. In this exercise, you're going to take the employee example from the last chapter and make it more modular. Split it into 3 files like we just did with the stack example. So you need to have a header file which will define certain functions of things that you want to do with employee structures. Employee.c will have the definitions for those functions, and lab6.c will be a test program. Now, I'm giving you, as you'll see on the next 2 slides, employee.h and lab6.c, so you don't have to sit down and figure out what should I name my functions and how am I going to do this? All I really want you to do is to provide the function bodies for the functions in employee.c. So take a look at the next slide. You'll see employee.h, and I'd like you to do employee.c and implement those functions. Now, in order for this to work, you're going to have some private data. Again, similarly like we did in the stack example. You want to have an array of employee structures defined privately inside of employee.c. Here are the functions that I'm declaring for you to implement. Add employee, and what it will do is it will begin a dialogue with the user. Just like you did with the previous program, you'll print out a prompt and read in the last name and the first name, etc., and fill in an employee structure, and then take that structure and put it into the array of employees, which is private to your employee.c file. Print employee will take an integer argument, which represents the index of the employee you want to print out, and so of course it has to be within the correct range from 0 to the number of employees that have been entered. And in fact, you want to also provide a function called numEmployees, which returns that number. So this is all patterned after the stack example that we've seen. Here's the test program. As you've seen before, the first thing we do is include employee.h so we can use its functions. And I'll just go through and add some employees. It's an endless loop like you had in the previous chapter. So whenever you type in a blank last name, then it'll return -1. That's the way you should implement add employee. And then I'll just go through a loop which will go from 0 to the number of employees and call the print employee function.